Thank you very much for the introduction. So I'm Chong Si. I'm very glad to be here to present my work, Face Mic in person. So this is a joint work with Tianfang Zhang and my advisor, Dr. Ying Shen at Rutgers University, and Xiangyu Xu and Jiadi Yu at Shanghai Jiaotong University, and also Peyton Walkers and Detached Cessner from Texas A&M University, and Yi Wu and Jian Liu from University of Tennessee, Knoxville. So with the capability of creating 3D worlds where the users can immerse in and interact with, augmented reality, virtual reality have attracted millions of users, and the market size is expected to reach $12 billion in the next 2 years. Such rapid expansions facilitate a broad range of emerging mobile applications, such as gaming, virtual shopping, banking, healthcare, and education. As the AR/VR domain extends beyond gaming, the control logic of AR/VR applications have been largely shifting from controller-dominated interactions to headset-dominated interactions via voice user interfaces. Well, as the AR/VR headsets are closely mounted on the user's face, we found that when the user uses voice user interface, the headsets are susceptible to the facial vibration caused by human speech, which encode with rich speech and speaker characteristics. Based on this key insight, we designed an eavesdropping attack that leveraged AR/VR motion sensors for eavesdropping attack. Our idea is to leverage the built-in zero permission motion sensors, including accelerometer and gyroscope, to capture human speech, and also speaker identity informations. Accessing this motion sensor does not require any permissions. This is because any AR/VR heads need to utilize the motion sensor to sense the user's head movements and simulate the corresponding motions in the virtual world. We found that facial vibration can capture the various identity information, which can be associated with the watching shopping preference, AR/VR travel history, and app usage behaviors. The facial vibration can be used to detect the gender of the victim, which can be utilized to advertising gender-specific products and analyze gender-specific behaviors of the victims without any user permissions. More devastating, we found that the facial vibration can leak speech-related information, such as social security card number, phone number, passport, transaction, and healthcare information. And exposing such information will lead to devastating privacy leakage for the victim. We found that there's two types of facial vibrations can be captured by the AR/VR headsets. The headset can be moved and rotated by the user's facial muscles when the user speaks, which encode with biometrics such as the face shape, tissue property, and muscle behaviors during speaking. And we refer such facial vibration as facial muscle movements. The headset can also capture the conductive vibration propagated through the user's cranial bone and vibrating the headset. Such vibrations are caused by the vocal cord vibrations, and we refer such vibration as bone vibrations. To study the distinctive characteristics of these two types of vibrations, we conduct a preliminary experiments by asking a subject to wear an Oculus Quest headset and speak some simple digits, 1 and 0. Then we use the accelerometer to capture the vibration signals and apply time frequency analysis upon the motion sensor readings. And we find that the motion sensor readings have a high strong response across a wide frequency range of 0 to 500 Hertz. We further conduct another experiments by asking the user to perform facial muscle movements without pronouncing, and we find that the high frequency part disappears. Based on this information, we can find that facial muscle movements mainly impacts low frequency motion sensor readings below 100 Hertz, while the bone vibrations produced by the vocal cord impact high frequency signals of the motion sensor readings. So to launch the eavesdropping attacks, the adversary needs to install an app on the victim's AR/VR headsets. This can be done by fooling the victims into installing the app or posting the app on AR/VR App Store. The app will collect motion sensor data in the background and sends the data to a remote adversary for data analysis. By applying deep learning-based method and signal processing techniques, the adversary can reconstruct the victim's speech information from the motion sensor readings and also infer the victim's gender and identity. Based on different training requirements, we summarize 3 representative attack scenarios. For the first scenario, we assume the adversary has the victims labeled and motion sensor data ahead of time to train machine learning models. This scenario is realistic in some case where the adversary can collect audio data from the victim. For example, when the adversary is communicating on a shared audio channel with the victims. For the scenario 2, the adversary does not have labeled from the victims ahead of time. In this case, the adversary can try to use unsupervised domain adaptation techniques to adapt a model pre-trained on other people's data to the victim's feature space. Well, for the scenario 3, the attacker wants to launch the attack in a real-time fashion. In this case, the adversary will not have any data to train the machine learning model. And in this case, the adversary directly applying a pre-trained model of other people's data to the victim for the inference task. To perform such an eavesdropping attack, the first step is to detect the human speech. As we know, for the AR/VR scenarios, the body movements may contaminate the motion sensor. Well, we found that the body movement may impact motion sensor reading at the low frequency part, so that it will be more reliable if we leverage the high frequency boom vibrations for speech detections. So we first, for our speech detection and segmentation scheme, we first calculate the short-time Fourier transformation spectrograms across the 3-axis motion sensor, and then accumulate their energy over 100 Hertz, where the boom vibration resides. And then we use a thresholding-based method to segment the region associated with human speech. So as we show in the previous, as we discussed, the body movements may impact the motion sensor readings. Well, although we can, the high frequency boom vibration may not have a strong impact interference, but for the low frequency part, the low frequency facial muscle movements have an overlapped frequency range with human body movements. So we need to denoise such motion artifacts. So how can we do that? A straightforward solution is to apply high-pass filters, but it is difficult to find an optimum cutoff frequency. This is because the body movements are mixed with the low-frequency facial movements. So we model this problem as a regression problem, which is to estimate the clean motion sensor data based on the noisy motion sensor data. We aim to derive a mask, in this case is MS, that can apply to a noisy motion sensor reading to attenuate the sensor readings of the human motions. To train such a regression model, we collect 2 sets of data. One set of data of human speech without motion, and another set of data with only motion. And then we mix these 2 types of data to generate the training data. And the target regression variable will be the data without motion, with only speech. By training such a regression model, we can estimate the clean motion sensor data based on the noisy ones, so as to denoise the motions, the impact of human motion. We extract 2 sets of features based on facial muscle movements and boom vibrations. For the facial muscle movement, we apply 3D speed. We apply numerical integration to calculate the 3D speed and displacement based on the accelerometer readings and gyroscope readings. Here is 2 spatial features we extract based of the speed and displacement from 2 users, and we can find that they're distinctive, meaning that they can capture biometric characteristic associated with each individual user. And based on the acceleration, speed, and displacement, we extract 11 time domain feature and 2 frequency domain feature to capture characteristic of facial muscle movements. For the bonbon vibration, we directly apply the spectrogram as the feature to capture high frequency pattern of speech. We designed 2 convolutional neural networks to process the data from facial muscle movements and bonbon vibrations. And then we derived the victim's gender and identities. So to process the data of facial movement, we used 3-stack convolutional neural network. And for the facial vibrations, we processed the spectrogram with 2 convolutional layers and also with a max pooling layer to reduce the feature size. And then we concatenate the feature map of the facial muscle movement and bonbon vibration and fed to 2 classifiers for gender detection and speaker classifications. Speech recognition is a much challenging task. This is because there are rich speaker-dependent characteristics encoded in the facial vibrations. If we have the label data ahead of time, we will correlate the labels, the speech informations, with the facial vibrations. Well, in the case, the label data is not available, we will use an unsupervised domain adaptation techniques, which transfer the representations learned from other people to the victim's feature space. We use an adversarial domain adaptation techniques to facilitate this task and remove the speaker-dependent characteristics encoded in the facial vibrations. So let's put everything together. So we assume a malicious app installed on the victim's AR/VR headsets, and we collect the motion sensor data and perform the data segmentations. We also perform a deep regression model to denoise the motion sensor data to remove the motion artifacts from the sensor readings. Based on the facial muscle movements and bonbon vibration, we extract 2 sets of features to capture these 2 types of facial dynamics. We design a deep learning-based frameworks to derive the victim's speaker identity, gender information, and also speech contents. If the victim's label data are available ahead of time, we will train the machine learning model using label data. Otherwise, we will apply unsupervised domain adaptation techniques to remove the speaker-dependent information encoded in the model. We conduct extensive experiment by using 4 mainstream AR/VR headsets, including 2 high-end standalone headsets, Oculus Quest and HTC Vive, and 2 cardboard headsets with different smartphone models. For the speech content, we collect data of 11 digits and 20 PGP word. The experiments involve 45 participants, and the sound pressure level is around 70 dB, which is a normal speaking level of using voice user interface. And the experiments are conducted in 6 environments, including 3 university office, 2 residential apartments, and 1 outdoor environment. So for speaker identification, it is encouraging to find that our attack can achieve over 97% accuracy and 93% accuracy on Oculus Quest and HTC Vive, respectively. And our attack can achieve over 94% success rate for both 2 cardboard headsets, showing the effectiveness of the attack. For gender detection, for scenario 1, when we have the victim's label data, we can find that our attack can achieve over 99% success rate. While for scenario 2 and scenario 3, we do not have any label data from the victim. Our attack can maintain a high attack success rate of over 85%. For speech recognition, we can find that for scenario 1, when we have the victim's label data, our attack can achieve 99% success rate, and the success rate can still have a 93% success rate on low-cost cardboard headsets, which has much slower sampling rates. Well, for scenario 2 and scenario 3, when we do not have the victim's label data for training, our attack can achieve over 54% success rate. for digit recognition, and the top 3 success rate are over 81% for the Oculus Quest. For the HTC Vive, the attack success rate are similar, but around 10% lower. Well, for the scenario 3, when we do not have any victims data for training ahead of time, our attack can achieve 42% success rate, which is much higher than the random guess. The random guess is 9%. So in summary, we propose the first of its kind attacks that leveraged facial vibration captured by AR/VR motion sensor to infer the sensitive information. And in addition, we find that the facial vibrations are dominated by 2 types of speech impacts: the facial muscle movements and bone vibrations. We designed a series of techniques to infer the headset wearer's gender, identity, and speech content. We also demonstrate the effectiveness of our attack, FaceMind, across 4 mainstream headsets, demonstrate that it is a real-world impact for the for AR/VR headset, which gaining rapid momentum in the recent years. So that's all.